Okay, hi. This is a talk about Lightning Talks, Lightning Talks. Lightning Talk is a Python tradition for basically it's 5-minute or less talks about a brief topic. The idea is that you concisely convey a topic, and if the audience gets bored, then you can switch. The next topic is coming up very soon. And I was challenged to do this by Brad over there, who suggested that I give it a shot. He wanted me to wear a cape or ring a bell between talks, but I don't have a bell. So I'll just sort of like wave when the talks change topic, or hope you can figure it out. So the slides you're about to see are available at this URL. So, and I'll show it on the last slide as well, so that if you want to go get the code samples, that you can see that. Talks the 7 talks is what we're going to cover. We're going to have ways to call out from Python, which is really good for those new to the language. An example using the weak ref module in the standard library. How to integrate Python with Emacs, the Emacs text editor, and the module for that called Babel, org Babel, that shows you how to mix languages. Use of the zope.schema module, which is popular within the Zope web framework community, but is usable without the web. How to intercept all method calls, a little bit of metaprogramming we'll get into here, a little more advanced. Then we'll get into creating an immutable type of your own, so that you can create instances that cannot be modified. And then the last one would be some examples of context managers in the Python language, how you would use them and how you would write them. So whenever people start using Python, they often are, if they're new to programming in general, or new to object-oriented programming, I should say, they sometimes aren't real clear on how a parent class and a child class interact, or how they should interact in a certain design of a program. So here we have a parent class called building, inheriting from object, the base class of the Python. And we have a child class called Moonbase that inherits from it. And some people, when they get introduced into object-oriented programming, they think that the child classes call into the parent classes. That's the way you're supposed to use them always. And so this is an example basically showing how the child class, which is sort of a specialization of the topic, where it's a moon base versus a Venus base versus a Mars base, and maybe there's some differences and such. So the specialization takes advantage of the general services provided by the parent class. So here we see how building.authorizes calls back up to this direction. This is an alternative way of doing it, using the super built-in keyword, keyword of Python. This benefit of this is it hides the name of the parent class. So here building is hard-coded, so if someone renames this someday, you'd have to go find these and change it. Here we don't hard-code that in. This also handles multiple inheritance, which is a big hairy topic separately from that, but that's just the two ways in there, but they're equivalent, and it's just sort of which one you find easier to use. So that's one way for the child to call into the parent and basically treat the parent basically as a repository of services that the children can use.
Why not simply use self.authorizes?
That would call back as long as there was not a child method also called authorizes.
What was the question there?
Oh, why not use self.authorizes instead of putting the class name on it? So if you did self.authorizes and there was no child method named authorizes, that would work fine. Yes. If instead you've overridden it and you want to call back to the parent, then you would need to put the class name on there, the parent class name. Good, that's right. Yeah. There's also cases where the parent class basically provides an overall algorithm for some calculation, and then you find the need to plug in pieces of logic into that algorithm, and this is a case for using a child class as well. So here the child class knows how to return the length and the width of certain attributes, and so the algorithm is up in the parent, and then we again basically plug in these pieces into it, and then when we call moonbase.footage, it will actually go up to the parent and then call back down into the child class. So that's an alternative way of calling the other, how you call the other direction. And here we do use the self length and self width. And then just the third topic throwing in is again, if you're not sometimes you have a need for calling with basically what they call computed arguments, where the purpose is to call plotter, and you want to pass in some positional arguments and some keyword arguments, and you're going to compute the list of arguments at runtime based on the environment, based on configuration. So here we have a list of positional arguments starting out, and we have a keyword arguments for media, print, and CMI. And then we can test whether you have a kitchen and add a positional argument, or add a keyword argument. So this is just give an example of how you would compute the arguments in a special case that you might need. Okay, that's one talk. Next talk. The weakref module is built into the Python standard library. It basically, in Python, you know that an object keeps a reference to another object. It's basically like keeping its finger on another object. Whenever you put an object into a list, the list has a reference to the other object. Weak references says, I'm keeping my finger on the other object in a less strong way so that if you delete it, then my weak link gets broken, it goes away. The purpose of that is to keep the object from being kept alive accidentally. So we'll see how to use that a little bit here. So say you have a member class, and he has a set of names that he's going to keep track of, members. And so we have the initialize, and we add himself to that. So the idea is to keep track of all of the vendor objects down here. We want the parent class to keep track of all of the child classes. So here we create a couple of the vendors, of the instances of it, and then we can look in the member.roster, and we can see that there are two objects in there, in the set, which is fine. We then go in to delete V1. We delete one of the vendors so that it should go away from Python memory. But because it's been added into this roster, it still stays around in memory. So even though we've deleted one of our vendors, his record is still hanging around in memory, and we would like to clean that up automatically without having to tell the collection, tell the set that vendor has gone away. So what we can do is we can put, instead of doing the add, we can do a weak ref of self here. Nothing else has changed. So basically, it's keeping its finger on that object, but it's keeping it in a loose way so that if the object goes away, we'll be notified by the Python language. So we have the two vendors here, and they show weak ref 2. There's nothing different about that, really. When we delete one, what happens now is when we look in the set afterward, we see that one of the entries is tagged as dead. So now we know programmatically, we know that there are some dead members and live members in the set. And we can actually test to see if they're dead and only print out the ones that exist, that are still alive. So by calling a weak ref and checking it for none, you can tell whether it's the object in question has gone away from memory. Even better would be to automatically remove it from our list because it's still taking up memory. The dead entry is still in our set. It's just tagged as dead. So you can also put in the Python using the weak ref a callback and have basically a callback to is dying. So here we register the self ref as before, but we pass in a little callable down here to a class method, and the method removes it from the set. You could also log the message or something in there, which could be very useful. And now when you delete the vendor, it actually does a callback and takes it out of the set. And maybe it logs, as I said, to tell you that this object has really gone away, and that could be really useful for debugging or maintenance. It's a great way for managing caches, where the cache keeps references to objects around, but when the originals go away, the cache should forget about them without a lot of work. So weak ref is good for that. Okay. Next topic.
I have a quick question there.
Sure.
What would be the reason not to do it in the first place?
Not do tracking of references? Oh.
Why we don't have the weak references in the first place? Because when you delete an object, I mean, you don't want to have. I was just kind of wondering.
Why all references are not weak?
Yeah. I mean, is there a purpose of it? I mean, do you have any idea why somebody would use it?
Well, sometimes you do want to keep it alive. As in, if two objects are using this third object, even though he stopped using it, this guy still wants to keep using that object. Maybe it's a record, or maybe it's a constant, and such. So two or more people using something could still be useful. But in the case of a cache, you really want it where when he stops using it, take it out of my cache.
If all references are weak, then all objects in memory are immediately garbage collected and disposed of.
Yeah, sure. Yeah, they're weak. They're not going to be. It's not held on strongly. So whenever the garbage collector says, "I need more memory, let me clear out things," he will clear out the weak references. So that's why. Okay. Okay. Using Python and Emacs. Now, I don't know how many people use Emacs, but it's just an interesting idea, I think. Basically, in Python, it has this org mode, organizational mode, that you can place into any plain text document with other stuff mixed in, these kinds of lines. Begin source Python, put in some Python code, and you can say the results are being output. And then whenever you double-click or hit a key on that range, it'll actually pop into your document the results of that. And every time you activate this, double-click on this, it'll refresh this. It'll delete and then rerun that piece of code. So it's good for teaching. It's good for experimentation with little pieces of Python code to be able to play with those in your document. And then you can do, it lets you put other languages in there as well. So here we can actually put in like shell documents and shell commands and such for those who use Unix flavored systems, and it prints the results out. Nothing unusual there. So that's the neat part. You can put Ruby, you can put Perl, you can put Python, you can put all kinds of other languages into this. About 25 different languages you can put in here. So it makes the documents become sort of a multi-language in your document. Here you can actually put in like data. You could have captured the data and give it a name in here. And then in your code here, you can write the Fibonacci series in Python. And you can reference the recursion and such. And then we can also mix in here a little bit of Emacs Lisp. And the Emacs Lisp is actually here, inputs are equal Fibonacci inputs. So this Lisp code is going to operate on this text table in the same document. And then the Lisp is going to call out to the Python code to finish the processing of the Fibonacci series. So you can tie languages together. And so one of the examples is like here you have the shell where you're collecting a live documents, information on the file system. You can actually parse out here the number of disk space used by the number of blocks, storage blocks used by these directories. And then you could pull it into the R language, which is a powerful statistical language, plotting it, and then you can actually input in the link to the graphic into your Emacs document, and then hit a key whenever you need to see it, and it'll actually show the graph. This is supposedly great for scientists who need to provide their data analysis, fragments of code, graphed results, and the text around their study all in the same document, so they can give it to a coworker and say, this is my analysis, please rerun it again and check the results, or you can see how I got my answers. And so this is what's good for, it could all be all Python for us Pythoneers, kind of thing. Anyway, it's a very useful feature for repeatable results analysis, basically. So you can repeat the results, the research is not done. So, okay. Next topic. Zope.schema is Zope is one of my favorite web frameworks, but this has nothing to do with the web. Basically, it's packaged as Zope.schema out there in the Chi shop. It provides extends interfaces so for attributes, for features of the attribute. So instead of just saying an attribute is a name, you can give it length, type, things like that. We'll see. Specification of features. It also can validate the input. So if you've tagged this attribute to be an integer and you set it to a string, it'll give you an error. So you sort of like typing, strong typing in some sense. It also will generate forms. So you can actually say, given this object, generate me a HTML form or a Qt form, and it will provide those fields with the right lengths and such. It's well supported in Python 3 and PyPy, so it's been around for a while. It's not old. 100% test coverage. So one of the examples is here. So you define the interface schema, and so you say title, which is your attribute, and we say that's going to be a line of text. It's going to have a title that's going to be displayed, say, next to the widget on the input. This will be like the bubble text that pops up, the bubble help, and it's required. And then you can go down here and see a similar one, and you can also put in like a constraint for a regular expression. It says, okay, this is a zip code. It has to be 5 digits - 4 digits. You can provide those kind of limitations on your data. So when anyone sets it to something that's not that requirement, it'll fail your program. And then to use it, you simply create your class and say it implements that interface, and set your normal putting your arguments into it. And then down here you see an example of a user group, and we can go and iterate all over the fields inside the definition and bind it to the actual user group object here, and then we can actually validate. And he'll actually complain about, this is an integer or string type mismatch. So anyway, it's just a way of providing a little typing on top of your Python attributes that can be useful. And it's very, very little, it's a small amount of code in Zope.schema, but it's very neat. And you can also, here's another way of fetching it out, bind and validate per field, so you can do that. Okay. And characteristics are that you can every attribute can have a title, a description for tooltips, the required read-only. You can set default values. So if the attribute's not provided, it's computed or defaulted. So here we can say if someone doesn't provide a date, it actually defaults to today, sort of like a SQL column that defaults. You can pass out ordering so that you can see how the fields are laid out on the screen. And then some of the fields also support additional ones, min-max values. Integer must be less than 10 or something, or lengths where it's less than 16 characters. Key type and value type says it belongs on the dictionary or the where it fits. And then there's the other kinds you can have is the ones you saw, text lines, password, where whenever it displays it in a widget, it puts asterisks there to hide the value. You can have all the normal Python types in there. And you can have actually a choice where it pops up and says it's a list of A, B, C, and nothing else, mixed multiple choice questions kind of thing. So it has to be one in that set of operations or set of values. And you can do dotted names for Python, like zope.schema or something. You can have it there and an ID. See what we're doing. Okay. Yeah. Okay. So anyway, zope.schema is pretty cool. Next is intercepting method calls. So suppose you have a class here called paragraph, and it prints some lead-in asterisks by default. And we would like to, outside the program, we would actually like to know when this gets called, and we'd like to know what the arguments going in are and what the result code coming back is. And so what we do is we can put trace calls class decorator around the class, and that will automatically basically wrap all the methods in the class in such a way that we can log or validate their results. So it saves you the trouble as a programmer from going in and actually putting in print the input, print the output of several hundred methods, say, for your class. And so now when we instantiate paragraph, when we call the lead in, it'll say, I called this method, and I was passed these arguments, and I got the result of this. So you sort of do that. So how do we implement that? How do we actually put that in our program? So the way to write your interceptor is you define a trace calls and you as a class decorator here, taking in the class that it's wrapping, and you put in there your own little get attribute. So every time it looks up an attribute in the class, like when it looks up the method to call, we're going to do something with that, and then we're going to replace the class attribute, the official get attribute, with my version of it. And so what we do inside there is we want to look up the attribute that he's asking for, because some of the attributes might be method calls, but some of them might be data elements. We only want to wrap the method calls. We don't want to wrap data elements. So we're going to get the attribute that he's asking for and get it back over here. And then we're going to find out if it's callable or not. And so if it's not callable, we're just going to return it unmodified, unwrapped, unchanged, because we don't want to get involved if it's a data element. But if it's a method, then we're going to get involved. We're going to put a call tracer around that method call and return that back to the user. And then what the call tracer does is he's a separate function over here that takes in the function that he's wrapping that's being called. And this basically is a closure. Let me switch over here. I think the class definition is a little bit easier. They're exactly equivalent. So we can have a call tracer object. It gets initialized by here's the class being wrapped. Whenever the method is being called, this is what gets called, passed in any number of positional, any number of keyword arguments. And we go ahead and call it. So we get the arguments and get the return code, and then we can here log out the arguments passed, the keywords, and the return value. You could put any kind of log trace here you wanted. You could check it for acceptability. You could do anything you want with that. And then we return the code. So that just wraps the calling of that method. This over here uses what's called a closure in Python. It's a little more advanced, but it's less code, as you can see. So over here, we simply have a function called whenCalled that just is equivalent to that, does the same operation, and we return that. So it's basically returns the wrapper, and then whenever later when the method gets called, it goes into that closure. You don't need to understand closures at this time, but yeah, they're equivalent. So. All right. Number 6, creating an immutable type. A type in Python, as you know, has immutable and immutable types. List are mutable. You can add elements to them. Tuples are immutable. Once you've created them, to enlarge it or shrink it, you have to create another tuple. So sometimes you want your own immutable types. And this is a pretty simple one. Basically, you create an immutable type by subclassing an immutable type. And basically, this happens in the object.new. Now, in Python, there's the object.new, underbar new, allocates memory. Underbar init fills the memory. And so those are the two stages. Because this is immutable, we cannot fill it after we created it because it's immutable. Filling it would be writing to it, and that's what immutable can't happen. So we have to fill it at the time we allocate the memory, because we only get to do it once. And so here we have something I call a tumbler. It basically is a dotted series of numbers. It's like the Dewey Decimal System or the chapters in a book. It's just something I was using in a program one day. And so it seemed to be suit that tuple. I wanted to pass in a string and then store that as a tuple of integers. So I have a new method. It takes in the class. This is a class here because we don't have an instance yet. We don't have a self yet. We're allocating the self. And we pass in the string of digits up here. This is just for the program I'm using at this time. We're splitting those digits based on the period. So we get back a list of integers, of strings. And then we call map, and we run each of those strings, the string of 1, the string of 3, the string of 2. We run that through the int function. So we get back here a list of integers. And then we simply call tuple and tell it to give me a tuple, and we're going to pass you this list of digits, which is it thinks of it as it's a list. It turns it into a tuple. It's a sequence. And we return that. And now that what it returns is a tumbler, not a tuple, and it is immutable. So now nobody can go in and edit or delete those things. You cannot provide an init method because you would get an error from the Python language if you did, because you would say it's immutable. You can't modify this object. Under new? Here? No. You might be right. Yeah, I'll have to check that. I think you're right, yeah. Yeah, darn, I got to check that. Okay, sorry.
I mean, you can still have the under init method. You can still have it, but it just can't modify your object.
Well, that's true. I guess you could have a stub or print something. Yeah, that's true. But if the init tried to touch it, then it would say attempt to modify a mutable object. Yeah, you're right. Yeah, that's good. Okay, how are we doing? Good. Context managers in Python. One of my favorites that got added to the language back in 2.5, or I think, but they're catching on. Context manager is the with keyword. So that's what it says with a file, and you can use the word open, they're equivalent in the language. Open this file in writable mode and store it into F, and then run this body of code, this nested clause of code, and we're going to write something into the file. If we leave the nested range of statements, we want to close the file automatically to avoid running out of handles and to make sure our data got written to the file. If an exception is raised, we want to make sure we close the file. That's why we don't just do open, write, close, because if an exception occurs on the write due to some complex expression we're writing, we would never get to the close. We'd raise the exception and leave. So a context manager makes sure that we're going to close, we're going to finish the context. We're going to close the context, which in this case is closing the file. Another place you use it is for like transaction manager. It's out there in the community for rollback and commit, abort, kind of things. And so basically here you can start a range of statements as a transaction, do some work, and you can either abort it based on some condition, or if an exception was raised, you want to roll back all those changes. And this can be databases or other data structures that maybe you wanted to roll back. And so that's a good use for context managers. Another one is for timing. So you have like with timer as T, you do some sequence operations, and when you come out, it actually computes the elapsed time for those statements. So context managers are very useful for lots of things. For threading, with lock, acquire this lock, do something, release the lock. Use a lot in the threading stuff, our message sending and such. So that's the uses of it. How do we create our own if we wanted to? How does it work? So here's an example of how the file is implemented. So we have the file, and this is overriding the current file. You wouldn't actually create your own file, but you have to create something of your own, like my file, because otherwise you'd change the Python built-in file object, and you wouldn't want to do that. Anyway, class file, and so you have the init that simply stores, say, the arguments that we're going to pass in, and then it has the enter method and the exit method for coming into the context and leaving the context. Any class that has those two methods is a context manager. It can have all kinds of other methods, but if it has those two, it's a context manager. So it calls these when it comes in on the with statement, and in this case, it's simply opening the file, remembering what it is, and then returning it. So that's what gets returned back as the as-f. When we leave, we come back in and we close the file. And it passes in these 3 additional values that indicate, are we leaving without an exception, everything went fine, or are we leaving as a result of an exception? Because it may matter on the closing of the context. You may want to clean or log something. So, and regardless of whether you have an exception, it's going to tear it down. In this case, we're always going to close it. In this case, and you can optionally return false or true. None is false. So in this case, it falls out and returns none, and that allows the exception. You can actually suppress the exception, meaning I captured it, I handled it. Don't tell the rest of the world. Don't mess up control. Yeah. An ABC, abstract base class? Don't know. Yeah, I haven't looked at ABCs much. Yeah, yeah. So this is the way you would define your own context manager using a class. However, there is a way to avoid a class and define it simpler. It conceptually is a little harder, but programmatically it's a little simpler. Okay. What it looks like is this. So in the standard library, there's something called the context lib. You return a context manager, and you create a function, and you put that as a decorator on the function. And takes in the same arguments. And here is the before code, the context open or start of the context. So we're going to open the file. And here down here is where we're going to close the file. So that's the inner context, and that's the exit context. And the way they did it was they used the iterator protocol, where we use the yield here. So basically, it's going to run the code into here, and then it's going to run whatever body of code you had within the with statement. And whenever it comes back out here, then it's going to go back and finish it. So I said it's less code, but you got to understand iterators, and that may be a little harder. And we want to put the exception around here because we want to make sure we close it no matter whether we got in here with an exception or not. Because if you leave off the try finally, which you sometimes see people do that, which is bad because that's a broken context manager. Because if an exception is raised inside your with statement, you're not going to get to the close. You're not going to release that lock. So this is just another way to do a context manager. And that's the last one. So, and there's the URL for the slides. So hopefully something in there was interesting. So. And we got 2 minutes if there's any questions, or maybe we over. Okay.
Have you found anything similar to the Emacs bit for Vim or any of the other editors, or is Emacs only your only focus?
Emacs is only my focus. Yeah, there may be something. And Walker will be talking about the IPython notebooks tomorrow, I think, but which is similar idea of keeping your data together. Yeah. So, any other questions? Okay, we'll let everybody get in here and get seated. So, okay, thank you.